In this lecture, we are going to learn about traveling salesman problem using branch and bound. So our main focus will be on branch and bound method for solving traveling salesman problem. So let's get started. What is traveling salesman problem? So if you have, let's say, a graph GV comma E, so you have to find basically a tour or a cycle that covers all the nodes of the graph exactly once, and we start from any node and come back to that node. So A to B, B to C, C to D, D to E, E to G and G to A is a simple cycle here where we start from A, reach back to A, and this is a traveling salesman cycle. Okay, so our aim is to find the minimum traveling salesman cycle, the smallest cost. So again, the state space diagram, what is the maximum possibility that we can have? So if we take a small example, we have 4 nodes. So let's try to make the state space diagram. So don't be afraid of what is state space. So basically it tells what are all the possibilities. So we start from node 1. Okay, and in any cycle, so you can start from any node can be taken as the start. Okay, so we take node 1 as the starting point. So from node 1 I have 3 possibilities in the graph. Okay, I can go to node 2, to node 3, node 4. Of course we have to look for the edges, but in general this is the case. From node 1 I can go to node 2, node 3 or node 4. Okay, then we come to node 2, and if we have already traveled the edge 1 to 2, then what are the possibilities for that cycle to complete? I can go from 2 to 3 or 3 to 4. If I take the 2 to 4, okay, so what happens? Then I have only one possibility. I have covered node 1, then 2 and 4, so I have only left a node is 3. So this is all the 4 nodes are covered. I start with 1, go to 2, from 2 I go to 4, from 4 I go to 3, and from 3 I go back to 1. So this completes the cycle 1, 2, 4, 3, 1. So this is a traveling salesman cycle, and of course I have to find the minimum cost cycle. Okay, so how many possibilities are there? So let's see some. So node 14 here, so it represents a tour. I start from node 1, then I take the node is 3, then from 3 I go to node 4, from 4 I go to 2 and then back to 1. Okay, so this is the tour. Then node 15 represents, I start from node 1, I1 is 4, which means I go to node 4, I2 is 2, which means from 4 I go to 2, I3 is 3, which means from 2 I go to 3, and then of course you have to go back to 1. So if the nodes are numbered from 1 to n, and Cij is the cost of edge ij. Okay, Cij is infinity if I comma j is not an edge, and we have n nodes. Okay, so let's see. Without loss of generality, we can assume every tour starts at and ends at node 1. Okay, so in a cycle, of course, everything is symmetric. You can take any one as the starting point, but then you have to reach the same node again. So that tour can be represented by node 1, then pi, and coming back to 1. What is pi? Pi is a permutations of the node from 2, 3, 4, 5, 6 till n, node n. So this permutations, how many possibilities are there? If we have n minus 1 nodes here from 2 till n, so n minus 1 possibilities, and if we have a permutation, so we have n minus 1 factorial permutations are there. But that size can be reduced because not all of these permutations, like, they are edges. Okay, so 1, I1, I2, I3 till in minus 1, then 1. This will be the this is the permutation, and this is valid permutation only if ij comma ij plus 1 belongs to an edge. So all these should belong to an edge, then only you can have a valid tour. Okay, so in branch and bound, what we do? So of course we saw that, okay, you search all the space and then you will have a huge cost. So what happens if we try out all the n-1 possibilities? So that is there, and then you have to check. So that algorithm will take O of n square to the power of n possibilities. Why? So because n-1 factorials were there, and that n-1 factorial is bigger than that 2 to the power of n. And now when you have got one tour, if I say like this, a permutation is given, then to check if it is a valid tour, so again it will require you time of n square. Okay, so if I have given you this tour, then you have to check in the adjacency matrix. So I have to check, okay, so for 3 to 4 is it present, 4 to 2 is it an edge, 2 to 1 is it an edge. Okay, so this we have to check. So this algorithm will take n square 2 to the power of n time. Okay, so you should understand n-1 factorial is greater than 2 to the power of n-1. So why will that be true? So n into n-1, okay, n-2 till we go to 2 and then 1. So each of these numbers, of course, after 2, so they are greater than 2. So this n-1 factorial is of course greater than 2 to the power of n-1. And then what happens when we have got a sequence, then you have to check from the adjacency matrix. Okay, so moving forward, now what we do, we say that, okay, only we will check for all the valid permutations where it belongs to an edge. Now in branch and bound we were talking, so we try to reduce those search space. Okay, so this was the search space, that there were n is equal to 4 nodes. So in the first, from node 1 we had all the 3 possibilities. If I have covered one node, then I have 2 possibilities left, and so on. So this is a permutation tree where we have n-1, n is 4, so 3 factorial, so 6 possibilities are there in this tree. So what you need to do is that in branch and bound we try to reduce our search space. So I don't want to search in all the spaces here, all the leaves, all the branches, but what I try when I come here, I try to find, so I want to minimize the cost of the traveling salesman cycle. So what I do, I try to find out, I'm here, what is the lower bound of my traveling salesman cycle. Okay, so I have not traveled any node, I'm starting at node 1. I try to estimate the lower bound of traveling salesman cycle. Let's say it is 25 initial estimate. Lower bound, it can never be lower than that. Okay, so I get an estimate of lower bound, it is 25 for my graph. Then what I do, now I have in a 4 node graph, let's say I have possibilities, I can go to node 2, 3 and 4. Again somehow I try to, for all these branchings, I try to calculate the lower bound of the TSP. Let's say I get somehow by calculation here, it's 28, 32, 55. So now this tells that lower bound after selecting this edge, it is 55. If you choose this edge, you will get a minimum lower bound of 55. Here I will get a minimum lower bound of 32. Here by going from 1 to 2, your lower bound will be 28. So what happens if you do a normal breadth first or depth first, then you will take this one, then this one, like this, depth first. In breadth first you go towards the depth, but in best first, what we do, we see that which node now is giving us as the best possibility, that is the best lower bound for traveling salesman cycle. It means it has more possibility of getting us a good result. because here I know whatever traveling salesman cycle will be after searching all this part of the tree will be at least 55, but here it will be 28. So we search the minimum node where the minimum lower bound is there. But again the $1,000,000 question is, how will you find that lower bound? So there we have a concept of reduced cost matrix.